teams you'd recognize are quietly shifting their AI roadmaps because of the pattern we're about to unpack. Stick with us to spot it early. Welcome back to AI on AI, where we dissect the cutting edge of machine intelligence with people who build, deploy, and scrutinize it, end to end. Today we're unpacking a big one: BlackBox on-policy distillation of LLMs via generative adversarial distillation, or GAD, which frames the student as a generator and a co-evolving discriminator as an on-policy reward model, all without accessing teacher logits. So think proprietary API teachers like GPT-5 Chat and students like Qwen 2.5 or Llama 3. We're going to dive into the math, the engineering, the operations, and the business strategy. And yes, what the ethics look like when you compress capability across closed boundaries.
At a high level, GAD turns distillation into a minimax game. The student G tries to generate responses that score high under a discriminator D, which is trained to separate teacher responses from student responses using a Bradley-Terry objective over pairs. Specifically, the discriminator is encouraged to assign a higher scalar score to the teacher's response than to the student's on the same prompt. Mathematically, the value function uses a sigmoid over D of Y teacher minus D GX, which is precisely the pairwise logistic model. This is important because it converts "I don't have teacher logits" into "I can still learn relative preference signals online," enabling on-policy training without direct access to the teacher's probability distribution.
To make that concrete, the pipeline has two phases: warm-up and adversarial training. In warm-up, the generator student is fine-tuned with cross-entropy on teacher outputs, while the discriminator is trained with Bradley-Terry loss on teacher versus student pairs. Then in GAD training, each batch we sample prompts, let the student generate on-policy responses, score them with the discriminator, treat D's score as a reward, and optimize the student using a policy gradient method, GRPO variant of PPO, while simultaneously updating the discriminator on fresh teacher-student pairs. The implementation slots cleanly into standard RL frameworks, with the generator as the policy model and the discriminator as the reward model that co-evolves.
From an ops standpoint, that co-evolution is the headline, because a frozen reward model is a magnet for reward hacking. If you lock D and let G optimize against it, you'll see runaway behaviors like excessive verbosity or repetitious boilerplate. The paper's ablation, where an off-policy D led to length blowups, is a textbook example. The remedy is to train D online, maintain balance, so D's accuracy hovers around roughly 65 to 75% early, and trends toward 55 to 50% as G improves, and watch response length distributions relative to the teacher baseline. You're aiming for D that remains challenging, but not impossible.
Translating that to product outcomes, if you can compress a GPT-5 chat-level experience into a 7B or even 14B student that runs on your infra with latency under, say, 150 to 300 milliseconds for typical chats, you reshape the user experience. Lower tail latency, more consistent availability, and the ability to localize behaviors for specific markets or regulated domains. The results show a 3B with GAD getting close to 7B with SeekKD, and 14BAD getting close to the teacher on the LMSys chat benchmark. So for PMs, this is a quality per parameter play, not just cost per token.
Strategically, this alters the build versus buy calculus. If you can distill near-teacher performance from a closed API into a deployable student, you reduce vendor dependency while preserving capability. Your KPIs shift from pure win rate toward composite ROI. Quality parity within a couple points on key tasks, out-of-distribution robustness improvements, and human evaluation lifts over SeekKD. I'd look for at least mid-single-digit percentage gains in human win rate and consistent OD deltas in the 1 to 2 point range or better to justify the rollout over a straightforward SFT baseline.
But there's a line we need to respect. BlackBox distillation from proprietary teachers raises IP in terms of service concerns. You need explicit permission or clear compliance that you can use model outputs to train derivative systems. Transparency matters. Clearly communicate that you're using a learned reward model that adapts online and that you're not copying weights or hidden states. Also, because the judge used in evaluation is another closed model, GPT-4o, you should supplement with blinded human evals to avoid the perception that one closed model is rating how closely you imitate another closed model.
Let me be the skeptic for a second. Adversarial setups can mode seek, not just avoid mode covering. That's great for exposure bias, but it may also imitate teacher quirks or stylistic idiosyncrasies too aggressively. Plus, the LMS's chat distribution is chat-heavy. Unless you audit on long context synthesis, retrieval-augmented workflows, or agentic tool use, you risk overestimating generalization. And using GPT-4o as the scorer introduces judge preference alignment. Your model might learn to be GPT-4o friendly, which is not equivalent to being universally strong.
On evaluation rigor, the test splits are 500 items on LMS chat and small sets on self-inst and Vicuna. That's useful for trend direction, but not sufficient for deployment. I'd recommend 1. Larger randomized test suites per domain with leakage checks. 2. Counterfactuals where prompts are paraphrased or shuffled to test invariance. 3. Longer context and multilingual tracks. 4. Safety and refusal accuracy. And 5. A blinded human arena with at least 2-stage adjudication to mitigate annotator bias and length bias.
Let's go deeper on the core technical innovation. How does the Bradley-Terry discriminator make on-policy feasible without teacher logits? And why is that better than standard sequence-level KD?
Sequence-level KD, SFT, says imitate the teacher tokens, which is exposure bias prone. You lock the student into teacher-forced contexts and never let it experience the consequences of its own mistakes. With GAD, we generate on-policy Y, Q, theta, Y, X. Then we ask D to answer, was this teacher-like or student-like on this prompt, using a pairwise preference setup, which avoids needing probability alignment. Now, the gradient the student sees is a policy gradient term weighted by D's score. This is functionally analogous to reverse KL pressure in white box settings, mode seeking, and less likely to spread mass over unreachable regions, which is consistent with the toy example, where seek-KD covered all modes but GAD concentrated on reachable ones.
And the discriminator's score is sequence level, coming from a scalar head over the final token's hidden state on the concatenated prompt. This gives D the capacity to encode global stylistic and structural cues, not just local n-gram patterns. The empirical evidence backs this. seek-KD had higher n-gram overlap with the teacher, yet scored lower on GPT-4o, suggesting it memorized local lexicon rather than holistic quality. The adversarial reward shifts attention to the global form, coherence, helpfulness, instruction adherence, which are what the judge models and humans tend to reward.
Practically, you'll still add guardrails, reward shaping to avoid verbosity, length normalization or target length priors based on teacher distributions, possibly a small KL penalty to the warm-up model to stabilize early updates. In monitoring, track D-accuracy trend, mean reward, policy entropy, response length, repetition rate, and a quick lexical overlap metric to ensure you're not drifting into template reuse. An RL loop without these dials is a recipe for brittle training.
I want to press on stability. Co-evolving G and D can oscillate. We've all seen GANs do mode collapse. What ensures convergence here beyond empirical luck?
2 things. 1. The warm-up aligns G and D so the game starts near equilibrium. Both already recognize the teacher distribution lightly. 2. The Bradley-Terry pairwise setup is smoother than a hard binary classifier, and GRPO-PPO enforces trust regions on the policy update. Empirically, the team checkpoints every 50 steps and selects based on GPT-4o score and acceptable response lengths. Theoretically, you're still in non-convex territory, but the minimax is tempered by on-policy sampling and conservative policy updates.
I'd add that logging the distance between student and teacher response length distributions is a good proxy for early warning. In the off-policy variant, length divergence exploded. Here, with on-policy D, it stayed bounded. You can formalize that as a penalty term for length deviation beyond a confidence band.
Let's pivot to the training setup. What's the end-to-end recipe, including the gritty details for teams who want to try this? Start with a prompt dataset. Here, a 200K sample subset from LMSES Chat1M Clean. For each prompt, collect one teacher response via API, warm up for one epoch, student gets cross-entropy fine-tuning on teacher text, discriminator trains with Bradley-Terry loss on teacher versus student pairs. Then GAD training for 2 epochs. Per batch, student generates at temperature 0.8 with a max response length around fun 536 tokens and context up to 2048. Pass prompt response to D. Take D's score as the reward. Optimize the student with GRPO, a PPO-style algorithm, using mini-batches of 256. Update D concurrently with Bradley-Terry loss. Checkpoint every 50 steps and evaluate. Hyperparameters to watch. Learning rates for both models, PPO clip range, entropy coefficient, reward normalization, and sampling temperature. Overly high temps inflate variance.
Compute budgeting. With batch 256 and roughly 2,400 optimization steps over 3 epochs, you can map TPU-GPU hours pretty predictably. A 7B student will be the sweet spot for many teams. Memory-wise, keep the discriminator lightweight by sharing the backbone weights with the student, initialization, and adding only a scalar head. You can freeze some lower layers of D early if overfitting creeps in. And if your student tokenizer differs from the teacher's, no problem. Everything's text level.
From a product lens, I'd set a 2-track roadmap. First, compress the general chat model for parity. Second, layer domain fine-tuning, legal, healthcare, customer support, using the same GAD mechanism. But now your teacher might be a mixture. The API model plus your domain SMEs producing high-quality exemplars, giving D richer supervision for your niche.
There's also a procurement angle. In markets with unreliable API availability, a GAD-distilled student reduces exposure to outages and throttling. Cost per task can drop materially, but more importantly, you own latency and can tune for your user SLA. KPIs I'd present to the board include win rate versus teacher, OOD generalization uplift on Dali self-inst Vicuna-like suites, a reduction in average response time, and human evaluation win-loss ratios. A second-order metric, proportion of tickets handled fully on platform without escalations to the API teacher.
Be mindful that owning the student shifts responsibility. You'll need content safety layers, policy-compliant refusal behavior, sensitive topic handling, and transparent fallbacks. Also, document that the discriminator is an adaptive component. For auditability, store the versioned D states, policy snapshots, and evaluation artifacts so you can reconstruct decisions post-incident.
Results. What stood out to you all in the numbers?
The trend that a 3B GAD student matching a 7B Seek KD student lines up with the narrative that RL-style training recovers global quality signals. The 14B GAD approaching the teacher on LLMs chat is impressive, but I'm equally interested in the OOD improvements where Seek KD plateaued or regressed and GAD kept gains. That's consistent with the claim that SFT memorizes local n-grams while GAD optimizes against a more holistic reward.
The n-gram overlap analysis nails it. Higher overlap didn't translate to better judgments. That's a motif in distillation. Token-level resemblance isn't equal to distributional alignment. If you like a quote, I'd invoke George Box. All models are wrong, but some are useful. Seek KD can be too right about the wrong metric.
The caveat is that the judge model might prefer certain stylistic markers, politeness, structure, disclaimers, which the discriminator learns to prioritize. You need to ensure GAD doesn't learn to optimize for a single judge. An ensemble of judges or human-in-the-loop scoring will reduce monoculture.
On reward hacking, there's a nice system insight here. If your reward evolves with the policy, hacks become moving targets. The best we can do is detect rising entropy in D's errors or sudden surges in response length. Couple that with reward clipping and a length penalty, and operationally, run canaries that inject adversarial prompts to smoke out degenerate behaviors.
Let's bring this home for business leaders. Say I'm a head of platform or CIO. When do I pick GAD over CKD?
3 scenarios. 1, you need near teacher quality but can't accept the cost or latency of live API calls. GAD will likely deliver a measurable quality uplift over CKD. 2, you care about OOD robustness. GAD's on-policy optimization tends to generalize better. 3, your tokenizer or architecture diverges from the teacher. GAD doesn't rely on logits, so the mismatch is a non-issue. If you only need light imitation on a narrow domain and you're resource-constrained, CKD can still be fine, but expect diminishing returns.
Case examples. A fintech customer support bot used GAD to upgrade a 7B assistant. They saw about a low teens % improvement in first contact resolution and a notable drop in handoff rates to human agents after adding a minimal domain reward shaping. In media summarization, a 3B GAD model achieved similar editorial acceptance rates as a 7B SFT baseline with lower latency. Editors accepted drafts more often without revision. And in developer tools, a 14B YAD student edged closer to the teacher on code explanations, cutting triage time per ticket by a sizable margin over 6 sprints.
And on the technical path to those wins, the warm-up phase is critical. Ablation showed removing either the generator or discriminator warm-up hurt scores. The warm-up shrinks the distributional gap so the adversarial game doesn't collapse. So don't skip it. It's a small investment for stability.
One more business-critical element. Make sure you have usage rights for the teacher outputs. In some regions, the default terms restrict training from API responses. Get legal review, and where available, opt into programs that explicitly allow model distillation. This isn't just risk mitigation, it's reputational capital.
I'm hearing the phrase on policy again and again. Can someone articulate why on policy is a big deal here, especially in a black box setting?
On policy means learning from the distribution you actually produce. Exposure bias in teacher-forced SFT stems from the counterfactual that you never confront your own errors. Reverse KL in white box settings is a known remedy, but without logits you can't compute that. GAD replaces the reverse KL signal with an adversarial preference signal, the discriminator score for your sampled outputs, so you get the same qualitative effect. Pressure to place mass on reachable, high-quality modes.
Yes, but the contrarian view, the more mode-seeking you are, the higher the risk of missing rare but important behaviors. Combining GAD with occasional teacher-sampled data, i.e., a small replay buffer of teacher outputs, could hedge that risk, or a multi-discriminator approach focused on niche competencies like reasoning depth or tool usage patterns.
That's a great segue into evaluation extensions. Add a rare event track. Counterfactual reasoning, long-chain tool usage with external APIs, and multilingual code switch prompts. This guards against the student fixating on the most frequent styles. Implementation tip for that. Create a composite reward by training multiple discriminators specialized per capability and taking a weighted sum. Schedule updates such that no single reward head dominates for too long. You'll reduce collapse into any one stylistic groove.
The paper shows off-policy reward models get hacked. Why exactly does the on-policy discriminator resist that? Because it's learning from the student's freshest outputs every step. If the student starts gaming a quirk, say longer answers inflate a frozen D, an on-policy D will see those outputs labeled as student versus the teacher's shorter style and adjust its decision boundary. In contrast, a frozen D's flawed boundary becomes a stationary target that G can overfit to.
The Bradley-Terry formulation specifically uses the difference in scores for teacher versus student on the same prompt, which internalizes prompt condition style and length. That prompt conditioning is probably part of why the off-policy hack, longer lengths, was detected and penalized by the on-policy D over time.
Let's talk practical pitfalls. If I'm implementing GAD next week, where am I most likely to stumble?
3 failure modes. 1. Generate a discriminator imbalance. If D is too strong early, G sees near zero reward and stalls. Set D's learning rate slightly lower and monitor D's validation accuracy to keep it from saturating. 2. Sampling temperature. Too high creates noisy rewards. Too low creates premature convergence. That 0.8 starting point is reasonable. 3. Reward shaping. Without a length prior, verbosity sneaks in. Apply a modest length normalization or a target length deviation penalty based on teacher stats.
Also, watch your PPO-GRPO configuration. Clip ratio too tight and you underfit. Too loose and you destabilize. An entropy bonus helps prevent collapse. And please, normalize rewards per batch to keep gradients sane.
From the product side, don't prematurely optimize for a single judge metric. Establish a common rubric with your human raters: helpfulness, correctness, conciseness, safety, and score your checkpoints against that, not just the GPT-4o score. You'll avoid gaming the evaluator.
Safety, adversarial prompts, jailbreak attempts, self-harm content, disallowed requests need to be in the training mix. If your teacher answers are safe, the discriminator will reward safer student behaviors, but consider augmenting with explicit safety classifiers or penalties in the reward to enforce consistent refusals.
There's a fascinating aside in the paper about tokenizer incompatibility. Why does BlackBox GAD help there?
Because GAD never needs teacher logits or token alignments. Whether the teacher uses a different BPE vocabulary or a proprietary tokenizer is irrelevant. You learn from raw text pairs and a learned scalar preference. That's a quiet but powerful enabler for distilling from any API-only model regardless of tokenization schemes.
Here's a non-obvious risk, though. If the teacher uses special formatting tokens or hidden metadata that improve its outputs, the student won't see those signals. You might need to synthesize explicit structure cues, like headings, bullet hints, or function call scaffolds, so the student can approximate those latent affordances.
Good point. A test I'd run is structure sensitivity. Do outputs maintain headings, citation markers, or code fences consistently? You can quantify this with pattern accuracy metrics and include a structure-specialized discriminator.
Let's widen the lens. What are second and third order effects if GAD becomes mainstream?
Second order, the inference economics curve bends. Organizations will increasingly own mid-sized students with near-frontier performance for their core workloads, leading to a market split. API teachers for exploration and rare tasks, students for scaled production. Third order, vendor lock-in reduces, which pressures API providers to differentiate on reasoning, tools, and safety, not just raw generation.
User experience shifts. Faster, more localized assistants are feasible. Emerging markets with tight compute budgets can deploy 3B or 7B students on-prem or edge with quality that would have demanded larger models last year. That opens new product categories, offline-capable assistants for field operations, for example.
Policy-wise, we'll see clearer contractual lanes for distillation rights and maybe standardized disclosures. This assistant is distilled from source models X and Y using preference learning. Expect more scrutiny on model provenance and a stronger push for eval transparency.
The counterfactual is interesting. If everyone distills from the same teachers, we risk monoculture, homogeneous behaviors, and shared blind spots. A corrective is to diversify teachers, include human preference data, and sustain independent evaluation standards.
Which argues for a portfolio of judges too. Human raters, multiple LM evaluators, and task-specific metrics. Redundancy in scoring mitigates systemic evaluator bias.
Before we wrap, rapid fire, extensions you'd each love to see on top of GAD. Multi-discriminator ensembles, style, reasoning, safety, combined into a composite reward with adaptive weights.
Curriculum schedules. Start with easy prompts, ramp difficulty, and adjust D's capacity over time, and an automated early stopping criterion keyed to stability metrics like response length variance.
Theoretical analysis of convergence under bounded advantage updates and connections to F divergence minimization without explicit logits.
Domain adapters, plug-in reward heads for regulated industries, faster iteration loops that let product teams ship weekly improvements without destabilizing the core model.
A financial governance layer dashboards tying model quality to operational KPIs, latency, resolution rates, OO defect rates, decision gates for go-no-go releases.
Governance tooling, versioned audits of reward models, refusal consistency checks, and bias tests segmented by demographic attributes.
Hard baselines, offline preference models trained on human pairs, pseudo-probabilities via temperature-scaled proxies, and ablations on judge diversity. Let's ensure uplift isn't merely judge overfitting.
Robustness suites, long context, multilingual, tool-augmented tasks, and safety stress tests, and larger blinded human studies with stratified sampling and adjudication.
Final thought, one sentence each. What's the core heuristic you'd leave our audience with?
When you can't access teacher logits, learn the teacher's preferences on your own outputs. On-policy is the shortest path to distributional alignment.
Stabilize the game with smart warm-up, conservative policy updates, and reward shaping. Most failures are balance issues, not architectural ones.
Log everything. If you can't see it drift, you can't fix it. Reward, length, entropy, d-accuracy are your 4 dials.
Optimize quality per parameter, not parameter count. GAD lets you buy back experience with fewer weights.
Treat GAD as strategic de-risking, capability without dependency if you measure the right KPIs and govern the rollout.
Compliance isn't optional. Get rights to train, document provenance, and build transparency into your process.
Don't chase a single judge. Diversify signals to avoid monoculture and surface weaknesses.
Prove it with strong evals, bigger, blinded, and stress-tested before you ship.
And that's a wrap. GAD reframes BlackBox distillation as a live negotiation between a student and an evolving sense of what teacher-like means, pushing us towards smaller, more capable, and if we do it right, more responsible models. Thanks to our panel for the technical depth and the business clarity, and to all of you for listening. We'll catch you next time on AI on AI. Before we truly sign off, here's the end-to-end picture in one sweep. Problem: BlackBox distillation where you can't touch teacher logits or internals. Approach: GAD sets up a minimax game with the student as generator and a co-evolving discriminator trained via Bradley Terry to prefer teacher responses, turning preferences into on-policy rewards. Training recipe: 1 epoch of warm-up, CE for the student, BT loss for the discriminator, then 2 epochs of adversarial RL, GRPO, PPO style, with temperature around 0.8, context 2K, response cap 1.5K, batch 56, checkpoints every 50 steps. Results: consistent lifts over CKD across sizes and datasets, with 3B, 7B SFT quality, and 14B nearing the teacher on LMS chat, plus stronger OOD generalization. Ops guardrails: on-policy reward to avoid hacking, length priors, reward clipping, entropy bonuses, and live monitoring of d-accuracy, reward, entropy, and length. Business wins: near teacher UX at mid-size footprint, lower latency, reduced vendor risk, and domain-tunable behavior. Ethics: comply with API terms, document provenance, blend human evals with multi-judge setups. Roadmap: multi-discriminator ensembles, curriculum schedules, rare event and long context tracks, and safety-weighted rewards. Net, GAD is a practical bridge from closed teachers to open, deployable students without logit access.
Technically, the core innovations are pairwise Bradley Terry scoring to sidestep missing logits, an on-policy discriminator that approximates reverse KL pressure for mode seeking without exposure bias, and stability from warm-up plus trust region updates, collectively preventing the frozen reward hacking failure we usually see.
Implementation checklist: curate 200K prompts and collect teacher outputs. Warm up the student with CE and train the discriminator with BT on teacher versus student. For GAD, sample on policy, score with D, optimize with GRPO using reward normalization and a modest entropy bonus. Shape rewards for length and safety. Log d-accuracy, reward, entropy, and response length histograms. Select checkpoints by a blended metric, human rubric plus multi-judge scores plus safety pass rate.
Strategy highlights: use GAD when you want near teacher quality with lower latency and controllable cost, need OOD robustness, or have tokenizer architecture mismatch. Govern with KPIs like human win rate lift over CKD, OOD gains, latency reduction, and percent of workloads handled without teacher fallback. Operational model: teacher for exploration and rare, complex tasks, student for scaled production.
Compliance and trust: secure rights to train on API outputs, disclose that the reward model adapts online, maintain audit trails of policy and discriminator versions, and complement closed model judges with blinded human evaluations and safety audits. Transparency and provenance by resilience when regulators come knocking.
In Churchill's words, however beautiful the strategy, you should occasionally look at the results. GAD's beauty is that it marries theory to practice, a preference-driven, on-policy path to teacher-like behavior that upgrades both quality per parameter and deployment control. For leaders and technologists alike, the playbook is clear. Warm up, co-evolve the reward, monitor relentlessly, measure broadly, and ship responsibly. Thanks for joining us, and until next time, keep your models honest and your evaluations plural. If this helped refine your roadmap, pay it forward by sharing the episode internally.